Morning, everybody. All right, so let's get started working on chapter 2. So we left off last time talking about significant figures and the rules for significant figures, and then if we're adding and subtracting or multiplying and dividing, what we're going to do. So adding and subtracting, right? We want to work with the lowest decimal places. Multiplying and dividing, we want to go with lowest number of significant figures. Oops. Share screen here. All right. So remember, for rounding as well, we round using just the leftmost digit that's going to be dropped. We don't continue down the chain. So if we have a problem where we have both multiplication and division and addition and subtraction, what we're going to want to do is wait to round until the very end of the problem. So if we look at this here, we've got 3.489 times a parentheses 5.67 minus 2.3. Okay, so because of order of operations, we're going to want to do what's in the parentheses first. So we'll take these two numbers and subtract them from each other. And we end up with 3.37. Now, I don't want to round this or drop the decimal to the 10th decimal at this step, because then we could end up accumulating what's known as a rounding error. So I'm going to keep the whole number, and I'm just going to put an underline on this 3 just to remind me that, that the only numbers that are significant is this and this. So from there, then I will take my sort of preserved significance with the underline and multiply it by the first number in the equation. And when I multiply these two together, I get 11.758. Now this thing has 4 significant figures. This thing, the way it's written, it looks like it has 3 significant figures, but in actuality, because we're only honoring to the 10th decimal place, it actually only has 2 sig figs. So then we know that we can honor 2 sig figs, 1, 1. The 7 tells this one to round up to 12. All right. So just, sorry, all my classes like coincide, they crisscross at the very beginning. That's about where we left off, right? Yeah, okay, good. So we haven't done base units yet. Okay, so in chemistry and in most sciences, the basic unit of measurement is going to be the International System of Units, or the SI units. So we can see them here. We use the British system in the United States, and it makes absolutely no sense, because it's like, how many quarts are in a gallon? How many inches are in a foot? How many feet are in a yard? How many feet are in a mile? There's no consistency to the numbers. So instead, we're going to switch our mindset over to the SI units, where everything is base 10. So if I want to go to a bigger unit, I'm just going to add a multiplier of 10. If I'm going to go to a smaller unit, I'm just going to divide by some sort of 10 factor. So base unit for length is the meter. If you're not comfortable with a meter, 1 meter is pretty close to a yard. So if you've got a yardstick or 3 feet, the other side of it is probably a meter stick. Mass, the base unit, it's a little weird, but the base unit is a kilogram, which has got a prefix in front of it, but that is in fact the base is a kilogram, not a gram. Time is seconds. Temperature is Kelvin. Volume would be in liters. There's other ones out there. We'll talk more about temperature when we get to chapter 3 and what that Kelvin is, but Kelvin is based off of a a degrees Celsius scale. It's just a shift of degrees Celsius. So it doesn't really directly relate to Fahrenheit at all. Okay, so where did these values come from? They used some fun equipment. The standard length of a meter is the distance traveled through a vacuum, speed of light, measuring a laser, okay. The standard mass of a kilogram is defined by a block that they have in the International Bureau of Weights. So there is actually a little block that they've measured and said, this right here is what a kilogram is. Everything else is based off of time, the second. They have this really big fancy clock. And it has to do with the radiation of cesium-133. So that's how they keep the consistency of that. So mass versus weight. So we talk a lot about, in the United States, we talk a lot about weight. So when you're going on a diet or if you need to gain some weight, you get on a scale and it pops your information out in pounds. That is not the same thing as mass, all right? The kilogram is a measurement of mass. Mass is how much matter the material actually has. So like how many atoms does it have to it? So if you have more matter, you should have more mass. Less matter, less mass. So more atoms, you're gonna have more mass. Weight, on the other hand, is a measurement of the gravitational pull on matter. So if you have the same amount of mass, let's say your body's mass, whatever that happens to be, and you were to go to the moon and measure your weight there, you would weigh less. So your mass would be the same. Ideally, if you ate and consistently kept your same mass, it would be the same. Your weight would shift though, because the gravity of the moon is much smaller than the gravity of Earth. So the pull is much less. If you were to go take your weight on, let's say the sun or Jupiter, really big planet, your weight is gonna skyrocket, all right? So weight will fluctuate depending on the force of gravity. Mass will always stay consistent. Now, we don't deal with situations in our everyday lives where our weight would fluctuate, right? Unless you're training to be an astronaut. That's really never gonna happen. So weight has probably treated you pretty well thus far. But we're gonna get away from weight and we're gonna move towards a measurement of mass because we're dealing with science and we want to be precise, right? And we don't want a little pesky thing like gravity determining how much matter we have. So when looking at this slide, I'm going to put the annotations on. When looking at this slide, we've got a bunch of prefixes. And the prefixes, you get to plug in front of the base units. So your base units, we said, was like liter, gram, well, they had it as kilogram, but gram is really the base of kilogram. Second, Kelvin, meter. So if I want to deal with a bigger unit, I can plug one of these bigger prefixes on. So right here between deci and deca, right in there, that's where your base unit goes. Okay. So example could be the meter. If I need to be using a bigger unit, I could go up on this. If I want to be using a smaller unit, I could go down. So let's look at some of these. A deca is 10 times the size of a meter, or a decameter is equal to 10 meters. Hecto, we don't see that a whole lot. Hecto is 100 meters, okay, or 100 of your base unit. Kilo, we use quite often, a kilometer, or might sound better as a kilometer. A kilometer is 1,000 meters, all right? Then we go to some of these bigger ones, a mega, like a megabyte, you know, back when our cell phones only had like megabytes of storage. Now we're in gigabytes, right? If you're not getting an iPad with 32 gigabytes, it's worthless, right? You want to be having 64, 128, okay? You maybe even are like, gigabyte what? I've got a hard drive at home that has a terabyte to it, right? So big numbers here, millions, billions, and trillions. Moving in the other direction, a tenth of a meter, or if I was to take a meter stick and cut it into 10 smaller pieces of pie, that would be a decimeter. And they've got it written as its word meaning, tenth, its multiplier, and then also the exponent multiplier. These two things, these numbers are saying the same things, right? If I took 10 to the 1, I would have to move my decimal over 1. If I do 10 to the 12th, you can probably guess this is going to have 12 zeros. Okay, so same thing there. A centimeter is a hundredth of a meter, right? Or a centiliter or a centigram is a hundredth. Think about a century, right? 100 years. A cent, like a penny, is a hundredth of a dollar. Then we've got milli. Milli is not a millionth, okay? Milli is 1,000th. Think about maybe some of y'all are millennials. I'm on the older end of millennials. You guys are probably on the younger end of millennials. But right, 1,000 years, a millennium, different things like that. We start to get smaller after. If you notice after this one and this one, so these are all increasing, if I look over here, by a factor of 10, right? Or one factor of 10. So it's 10 to the 1, 10 to the 2, 10 to the 3, okay? 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. When you get out of this range here, you can see the hops start jumping by a factor of 3, okay? So 3 sets of zeros. So if we look here, this is a million. To get to the next one, there isn't a 10 million prefix, it goes to a billion, all right? There isn't a 10 million, or I'm sorry, a 10 billion or 100 billion prefix, it jumps up to a trillion. So you can see the factors are increasing by 3 zeros outside. Same thing over here, the factors are decreasing by 3. So a milliliter versus a microliter. A microliter is a millionth versus 1,000th. Then we've got a nano. You know, you hear things like nanobots. And they're like, oh, we're talking about something really tiny. Well, the nano is actually referring to a billionth. We've got a pico and a femto. For this class, as far as prefixes are concerned, you will possibly be using these ones in homework. And this one here, you possibly will see them in homework and labs. So you'll have to reference, but I want you to know how to do these guys from your head, okay? So kilo to milli, I want you guys to be able to do from your head. And I will show you real quickly a nice way to remember kilo to milli. These annotations. All right. So the way that I like to remember this is King Henry died before drinking chocolate milk. Okay, King Henry died before drinking chocolate milk. Sometimes some of you may have heard this with King Henry died drinking chocolate milk without the before. I like to put the before in because that is our base unit, and we actually have to, if we want to use this as a hopping thing to convert, we need to make sure we hop through the base unit as well. So B is going to be your base. And again, base units can be meter, liter, gram, second, all sorts of different things, okay? K over here is kilo. Why are you doing that to me? Kilo. Henry is hecto. Died is deca. We've got our base unit. Drinking is deci. Chocolate is centi. And milk is milli. All right. The ones on the left here are the big units. The ones on the right are the smaller units. So I'm going to show you guys a quick trick for fast conversions with this. Whoa, hello, where did you go? Oh, you got so tiny on me. Come on, find the zoom in button. You're so tiny. Last of this. There we go. All right. I don't want last. So let's do an example. So we're going to do a different way of converting for within the metric unit. Within the metric units or the metric systems, it's much easier to convert. When we're converting within the British system, we're going to have to use dimensional analysis. But for this, we can just do some quick hops. So let's say that you told your neighbor, you're like, hey, I did something pretty awesome. I went out and I ran 0.025 kilometers. Like I had a big morning, okay? I ran 0.025 kilometers. And your roommate's like, I don't really know what that means, but it doesn't sound that dramatic. Can you tell me what that is in meters? Because I know meters roughly 3 feet. And they're like, yeah, I can help you out. So the way that we're gonna work this chart here is you'd want it written out like this. Given piece of information is in kilometers, so I'm gonna put a little asterisk next to my kilometers. I am trying to find this thing in meters, okay? So meter is a base unit, so I wanna get to here, okay? So in order to do that, I need to hop my decimal to the right 3 hops, right? 1, I have to get through Henry. 2, I have to get through died. 3, I have to get through the base. That's why I include the base in this, because it allows me that hop. So I need to take 3 hops to the right. My decimal is right here. So I want to hop it 1, 2, 3 hops. The new location is next to the 5. 25 meters. So now you're telling your roommate, okay, well, so yeah, I ran 25 meters. And he's like, well, you know, I mean, that's like not even halfway down the block. So you might want to try a little more next time. So changing out our scale or our prefixes sometimes can give us a better understanding of like how much a unit is. Because if I say 0.0000005 micrograms or kilograms, what does that mean? And I can convert it to micrograms to get something that maybe makes a little bit more sense. So let's do another one. I want you to try and do this one. So I'm gonna give you, let me close out of here. I have 68 million millimeters, okay? I want you to find how many, let's do kilometers. I want to find how many kilometers 68 million millimeters is. Right, so hopefully that didn't take too long because you have this sort of nifty King Henry. So we're starting with a millimeter. So a millimeter lives over here. We want to go to a kilometer, which is, I'm going to change colors here. So we've got our millimeter over here. We want to get to kilometer over here. So I got to do quite a few hops. I've got to go 1, 2, 3, don't forget the base, 4, 5, 6. Okay, 6 hops. Now look at the direction that you're having to hop. You're having to hop to the left this time. So honor that. You're going to the left. We've got our 68 million millimeters. My decimal lives here. I need to hop 6 over. So 1, 2, 3, 4, 5, 6. 68 kilometers. This is why the metric system is awesome and why, yeah, thumbs up to metrics. That's why if we can, start thinking more in the metric system, it's just gonna do you a lot better. And if you wanna get into more math and science or medical field, you're gonna wanna be in the metric system. It just is it's a lot better. Okay, so let's hop back over to our slides. As far as when you're going to choose a prefix, so you want to choose a prefix multiplier that is most convenient for that specific particular measurement. Pick a unit similar in size or smaller than the quantity you're looking for. So if we look here, there's an example, a short chemical bond is about 1.2 times 10 to the negative 10th meters. So written in scientific notation, has very, very little meaning to it because you know that there's just a bunch of zeros in a decimal, right? It's a very small amount of a meter. So if there's 2 prefixes that we could use, a pico or a nano, the pico is 10 to the negative 12th, the nano is 10 to the negative 9th. you always want to go with the smaller of the two. So if we look here, this is 10 to the negative 10th. This is actually slightly bigger. This one is smaller. You may be thinking, well, how is that smaller if it's got a bigger exponent? Remember, these are to the negatives. So the more negative you have, the smaller you are as a number. So we would want to use the pico to work on this value here. When I convert this thing into a picometer, which again, I'm not going to be having you guys do on an exam, but you may find it in the homework. But when I convert this, I end up getting 120 picometers. That number is much easier to wrap my mouth around than 1.2 times 10 to the negative 10 meters. It's also helpful in that if, let's say you know that the length of the length of a carbon atom is 44 picometers, then you sort of have something to like relate it to, as opposed to this here that's just so random and arbitrary. You always want to try and choose the smaller one. Yeah, because then if we use the smaller unit, we get rid of any like decimal here. So it's 120 picometers. If we had gone with the nanometer, it would have been 0.12 nanometers. So we try and go with the picometer or the smaller one. All right. Volume. So volume is a measurement of space. The SI unit for volume is the liter, but volume can be what's called a derived unit. A derived unit means that it's made up of other units. Area, length is not a derived unit. Length, let's see, let me write this down. I'm just not talking to myself. Okay, so length is a unit of like meter, right? That's not derived in that it's not more than one unit, it's just a meter. Area is an example of a derived unit as well. What is area? Area is, it has to be a length times a width. So your area would be meter squared. Volume is also, can be written as a derived unit. Volume is, think of a cube, a length times a width times a height, meters cubed, okay? So some examples of volume are cubic meters, cubic centimeters. So this one here, if you ever hear on like a medical show, give them 50 cc's. All right, that's what a cc is. It's a cubic centimeter. Cubic millimeters, cubic yards. If anyone does any landscaping and you get like 17 cubic yards, which is like, ugh, that just sounds like so much work. 17 cubic yards of mulch. That is also telling you, like, they don't sell you your landscaping mulch in area. They sell it to you in a sort of a volumed shape. Okay, so now we're going to move into dimensional analysis, problem solving, and unit conversions. So with King Henry died before drinking chocolate milk, you get to do the hopping, and that's fun and easy. Other problems won't allow hopping to occur, so we have to set them up using dimensional analysis. So this thing here says, let's say, getting to an equation, or to an equation to solve from a problem statement requires critical thinking. So what is critical thinking? Critical thinking is your mind's ability to look at a problem and figure out what to do with it. I can't teach you critical thinking, but critical thinking is something that can be strengthened, just like any muscle in the body, or right, if you're playing the guitar and there's that like mind-body connection that strengthens over time. Critical thinking is something you can develop, okay? Critical thinking is the ability to not just replicate what an instructor is telling you, but any problem the instructor throws at you, you can say, oh, I understand this concept. I know how to get at this problem from different angles. So many of the problems throughout this class can really just be thought of as unit conversion problems. It's going from one unit to another unit. That's like what a lot of this class is. And you're given one or more quantities and ask them to be converted into a different set of units. There are some situations where you have a specific equation and that you wouldn't use unit conversions, okay? So an equation would be, hey, density equals mass over volume, and I'm giving you density and mass, you solve for volume. You plug them into the equation. So dimensional analysis is just a fancy way of setting up or saying that we're setting up our problems to convert units. Units are multiplied, divided, and canceled like any other algebraic quantities. Using units as a guide will help us to solve in dimensional analysis. You always want to write numbers associated with each unit. Always include units in your calculations. So don't ever just start writing numbers like up until this point, because we've been talking about sig figs and stuff, we've been saying, oh, 3.52, 8.7. Now we want to start giving those numbers like a unit or a value. So always write the unit with it. And then you'll divide and multiply those units until units that you want appear and units that you don't want disappear. And that all sounds very like ethereal. So let's look at maybe something a little bit more tangible, okay? So in a unit conversion problem or in dimensional analysis, you'll start with given information. You multiply it by something called a conversion factor. A conversion factor is something that has two values that equal each other. Okay, so 100 centimeters equals a meter. 100 centimeters equals a meter, 1 meter. That would be an example of a conversion factor. 12 inches is equal to 1 foot. That's a conversion factor. It's two things that are the same, but they're written in different units. When you take your given information, you multiply it by whatever the conversion factor is that you're using, you should be able to get your information sought or your find. It'll be written sort of like this. You'll have your given unit. You'll multiply by your conversion factor in such a way that the given unit is underneath your fraction bar. The desired unit will sit on top of the fraction bar. And what happens is the given units will cancel and you'll be left with the desired units at the end. So this setup here is like the money shot that we will just do over and over and over again throughout the semester. Even when we get into things that are more complicated like stoichiometry, where we've got moles and we've got different compounds, our math is still going to be following this. All right, so here's an example of a conversion factor. 2.54 centimeters is equal to 1 inch. You can write that in a couple different ways. You could write it like this. So we could divide each side by 1 inch. So we could have 2.54 centimeters over 1 inch. And this, because these two things are the same, right? Anything divided by itself is equal to a value of 1. Don't believe me? Let's do one here. 3 divided by 3 equals 1. 1.8 divided by 1.8 equals 1. Tuna divided by tuna should equal 1, okay? Because these things are canceling with each other. These two things don't have the same units, but they're equal to each other. They have different units, but we've already established that this is equal to this. So when you take those things over each other, they're equal to 1. So whenever we're using conversion factors, we're not changing the value of the number. We're just sort of shifting its units. Okay, so if we look at a problem here, let's say that you were given that you had 44.7 centimeters, and I wanted to figure out how many inches it was. Well, we would know our conversion factor. Between metric and British, that stuff will be given to you on a formula sheet that you can use, so you can have those readily available. By the way that I'm gonna, excuse me, it is so Monday morning at 8:38 a.m. So the way we're gonna use our conversion factor here, we always write our given information first, and then we wanna situate our conversion factor so that the centimeter part is underneath this fraction bar. Why? Because then the centimeter will cancel, and what we'll be left with is inches. Those cancel, and then you just run it through your calculator. So I would take this 4.7, multiply it by 1, but you're not allowed to multiply it by 1, and then divide it by the 2.54, and you should end up with 17.6 inches. And we're not changing this value, and we're not changing this magnitude, because in theory, this thing right here is equal to 1. So we're just taking a number and multiplying it by a value of 1. We're just shifting the units. Your conversion factor can be written either way. So you can write it as for this specific conversion factor, you can write it as 2.54 centimeters over 1 inch, or 1 inch over 2.54 centimeters. You have that ability to flip back and forth. Why would you switch the flipping? It's depending on which direction you're going. So if you're going from centimeters into inches, you want it set up like this so that the centimeters cancel. If you were going from inches to centimeters, you'd want to use the other one where the inches are on the bottom. So why don't let's just go ahead and do an example of that. So let's say that we are given that we have 85.2 inches. And just for the sake of this class, we don't like things in inches, so we want to get this into centimeters. All right. And from that previous slide, I'll give you the conversion factor. 1 inch is equal to 2.54 centimeters. Okay. So go ahead and set that up in dimensional analysis. You may be able to say, well, I just know that I'm going to divide by this or multiply by this. Set it up in dimensional analysis, because they will get more complicated as time goes on. Okay, so when setting this problem up, I'm always going to start with my given information. And the problem isn't always going to be written like this, where it's given and what you're trying to find. You'll have to pull that out of a word problem. So, you know, get in the habit of starting to like underline and circle things. This is my given, this is where I'm headed, just to get in the habit of, I mean, what that does is that helps to activate your critical thinking skills. Because what I see students have trouble with is like they'll get a word problem and they just go, boom, they just shut down. I don't know how to do this. I'm not good at math. I don't know how to do this. Most of this stuff isn't very complicated math. It's multiplication and division. It's the critical thinking part of getting from the word problem into the dimensional analysis that gives people trouble. So set yourself up. Start with our given information. We have 85.2 inches. And I'm gonna, well, I'll do it one way first. So multiplied by our conversion factor. So here's our conversion factor. Now, when looking at this, you want to go with whatever this unit is, that's what's going to go underneath the fraction bar. So inch has to go underneath the fraction bar. Make sure you put the right value with it, 1 inch. Okay. The 2.54 centimeter will go on top, 2.54 centimeter. The reason that I need it to be this way is so that the inches go bye-bye, because I don't want inches anymore. I just want centimeters. If I had flipped this or written it the other way, inches would be on top, centimeters would be on bottom. What would happen to my units? It would be an inch times an inch, which would be an inch squared, divided by a centimeter. That's not a unit that we want to see. So make sure you're setting it up where they are crossing out. The only unit that will be left is a centimeter. We like that. So I'll put centimeter. I'm going to plug this into the calculator. See what we get. (85.2) times 2.54. So I don't think about, oh, I've got to multiply it or I got to divide it depending on which direction. I just set it up in my dimensional analysis and let it tell me what to do. So it says, take this number, multiply it by this, and divide by a 1. So I end up getting 216.408. The last thing we need to do is round this the correct number of sig figs. I'm going to tell you guys, conversion factors, these things, are not your limiting sig fig. You see how it says 1 inch? We would look at that and think, oh God, we have to drop to 1 sig fig. No, conversion factors think of them as having an unlimited number of sig figs. They're exact relationships to each other, so they aren't our limiting. It's usually our given information that'll limit us, okay? So this says I've got what, 1, 2, 3 sig figs. So I need to round to 3 sig figs, 216 centimeters. Yes, no, maybe so. So if you are converting and your unit using something like 1 meter is equal to 100 centimeters, this is not going to limit you to 1 sig fig. It'll be whatever your given information is. Just for the sake of this class, think of your conversion factor as having an excess amount of sig figs. Okay, so I'm going to do another one. Given that we have 1.8 kilometers, and I want you to find how many centimeters this is, okay? And I want you to try and do it in dimensional analysis. You may be thinking, oh, I'm going to pull my King Henry died before drinking chocolate milk out. For this one, try and do it in dimensional analysis, just to see how nice that King Henry is to be able to use. On a test, I'm not going to make you do it this way, but I want you to set it up in it. And you don't have to necessarily do just one step. So if you're like, I have no idea how many centimeters are in a kilometer, but I do know how many meters in a kilometer and how many centimeters are in a meter, you can do a multi-step problem, all right? Okay, so this is sort of one of those like wonky conversions. 1 kilometer would have 1 kilometer has 100,000 centimeters in it. That's not something that you necessarily know off like the top of your head. So you could do 2 conversions here. We could say, hey, I know a relationship between kilometers and meters, and then I know a relationship between meters and centimeters, right? So this is like a twofer. So you would have to take 2 hops or 2 conversion factors. I know 1 kilometer is equal to 1,000 meters. And I know 1 meter is equal to 100 centimeters. You may not know this yet. I know this, but you want to be able to reference these things. So this is called a flow chart, and the slides a little bit farther down show us this. It's just a way to get, again, set up our critical thinking skills. Here's our given, our find. Flowcharts help a lot. So I'm going to start with my kilometers. So I have 1.8 kilometers, and I want to move into meters. So I need to multiply by something to get me into meters. Well, this thing right here relates kilometers and meters. Here's a kilometer. I want to put the kilometer on the bottom and the meter on the top. And then just make sure you put the same or the correct values. So 1 kilometer equals 1,000 meters. Common mistake is students will flip the values. They'll get the units in the right spot, but they'll flip the values. So they'll say, hey, 1 meter is equal to 1,000 kilometers. No way. A meter is something you can walk in half a second. 1,000 kilometers would take you a little longer than that. Those are not equal to each other, okay? So this would get rid of my kilometers, and we'd have a value of meters. Some people will stop here, solve for it, and then work forward. I'm going to just sort of chain them together. So I'm going to multiply by my next conversion factor, which is meters to centimeters, this thing here. Here's the meter on top. I want the meter then to go on the bottom because I want to get rid of meters and get into centimeters. I'm going to put centimeter on top. 1 meter is 100 centimeters. What happens to the unit of meters? They end up canceling. So we get a value of 1.81234 centimeters. Yeah. 180,000 centimeters. Okay. So the way that this is written, you guys will probably start to see me write it more like this, 1.8 kilometers. And I make these like lines with boxes, 1,000 meters, 1 kilometer. Okay, if you see this, don't be scared by this. This is the same thing as that, just written a little differently. This thing is the divider bar. These are the multipliers. All right. So here's conversion factor 1. These two are the same thing. Here's conversion factor 2. Okay. Same thing. So you can kind of think of there being a little multiplier value right there, which is that right there. Questions on that? Outside of just needing to practice. Okay, let's do another one. Why not? Well, let's take a look at the slides. I forgot what's on the slides. Maybe there's something useful in there. If not, we'll just do another example problem. Okay, oh yeah, so it talks about a solution map is a visual outline that shows the strategic route required to solve the problem. So this is sort of what I've already been talking about as far as setting the problems up, but just ways of, again, massaging your critical thinking skills. So making these sort of boxes, where am I starting, where am I ending, how am I getting there? The little arrow between will be your conversion factor, okay? General problem solving strategy, again, already sort of brought this in, but always identify where you're starting. What is your given information? Identify the endpoint. What are you trying to find? What does the problem want you to find? Try and devise a plan to get from the start to the end. That's where the critical thinking really comes into play. Maybe make a solution map. It can look something like this. Here's your given, you've got a solution map, and then you find your answer. Great. Sort, strategize, solve, check, okay? So sort your information from the word problem, strategize, create a solution map, or create some sort of problem solving technique that's gonna work for you. Solve the problem, obviously, and then check. So one quick way to check is like, does this make sense? All right, does it make physical sense? So if you're converting from, let's say you have 100 centimeters and you're converting that to kilometers, and all of a sudden you went from 100 centimeters to like 5 million kilometers. That doesn't logically make sense. So you've probably moved your decimal in the wrong way. So solving multi-step problems, we already did a multi-stepper, but breaking it up into, maybe the original problem isn't quite digestible, but breaking it up into individual parts makes it a little bit easier. All right, so let's do a multi-step problem. Okay. And I'll write it as a true word problem so that you have to pick it out. How many inches are in 0.305 kilometers? So this is a multi-stepper, and there are different ways of approaching it, okay? So people kind of attack these conversions sometimes in different ways, depending on what information you have, what values you know. If you, for whatever reason, know how many inches are in a mile, I guess you could convert from inches to mile and then miles into kilometers. I probably wouldn't go that way, but it may look a little different than the people, we're not in the classroom, but the other people around you. So give it a try. Just another 30 seconds or so, and then we'll walk through it. All right. So I'm going to attack this. Well, I'll show you two different ways that I would maybe go about this. So the first one I'm going to do pure dimensional analysis. So I'm going to write my given information, which is 0.305 kilometers, and I'm trying to find inches. Okay. So getting in the habit of writing that out. Now for my people that are like, please, I took calculus like last year. I know my math. I'm not speaking to you, okay? I'm speaking to everybody else that's like, I do not know how to set these things up. Simplify it down for yourself. So I'm going to set up the way that I would go about it, just to know that I did it correctly. I would do kilometer to meter, meter to centimeter, centimeter to inch. Anyone solve it that way? No, less steps, more steps? Yeah, okay. The reason that I would do this is because all these conversions for me in my head are like really accessible. Like I just got them memorized. So that's why I would do that. I have to think about how many kilometers are in a centimeter. So I start with my given information of 0.305 kilometers. I'm going to put it into dimensional analysis. So the first step is to go to kilometer to meter. Don't even bring centimeters and inches into the book yet. Just go this hop here. This is all we're trying to do. So kilometers to meters, I know that 1 kilometer has 1,000 meters. So I leapfrogged to meters. Kilometers go away. I don't know why that made a triangle. This thing has like an auto snap thing on it. So it likes to make shapes when there aren't any. All right, next step is to go from meters to centimeters. So I know that 1 meter has 100 centimeters in it. Meters will cancel, okay? The last step is to get from centimeters into inches. So 1 inch equals 2.54 centimeters. Centimeters will cancel. So we end up with 0.305. So my calculator popped out 12,000, 7.874, something like that. I can honor 3 sig figs. Go off of what your given information is. Don't go off of your conversion factor. So 1, 2, 3. So I keep the 1, the 2, and the 0. 12,000 inches. Okay, another way we could solve this. This one will be a lot faster. So we're given that we have 0.305 kilometers. We want to find inches. So in this flow chart, I'm going to go kilometers to centimeters, centimeters to inches. And in this first hop here, I'm going to use King Henry died before drinking chocolate milk. Okay, so I've got kilometers to centimeters, kilometer here, hop 1, 2, 3, 4, 5 hops. So 1, 2, 3, 4, 5, 30500. That's in centimeters. And then the last step is to get it into inches. So for every 1 inch, I have 2.54 centimeters. Those will cancel. 0. And we end up with the same answer. Okay, you guys like 1 or you like 2? You like technique 1 or 2? You like 1, 2, 1, 2, 1. Okay, so it's gonna be different for different people. You go with what works for you, okay? You may find that 1 is more comfortable. It may shift later on. So we're gonna stop there for a minute. What I wanna do really quickly, let's slide share. Okay. I want to just put you guys out into some breakout rooms. I don't know if you guys done breakout rooms in other classrooms before. It's just a way for you guys to get into a smaller pod. I'm going to put you guys in probably 3 in each group so that you guys can get each other's emails in case you have questions, and you can just chit chat for a minute or 2 and see like somebody else's face besides mine for the class, but really get each other's information. So if you're working on labs or you have questions on homework and stuff, they may be somebody that you can reference, okay? So my people who don't have video on, you will maybe turn your video on and hi to some people. All right, so let me do this. Let's see if I can do this. 12 participants in how many rooms? If I want 3 of you, we'll put you in 4 rooms. All right, so they are created. So it will prompt you to accept, turn your mute off, and you can talk to each other when you get in there.
Done any science since I was like cool.
Hey, sorry, I'm just sneaking in. So,
Okay.
just make sure you guys get each other's info, okay, for a little bit of help.
Okay.
Cool. And when you guys are done with that, you can get off unless you have a question for me, okay?
Okay, thanks.
Hey, once you guys have gotten each other's information, you're welcome to click out of the class for the day and everything, okay?
Okay.
Cool. Thank you.
All right. Unless you have a question, then you can stay after and I'll chat with you, okay? Bye.
Okay. Bye.
Hey, just hopping in real quick. When you guys are done getting each other's information, you are welcome to leave the lecture for the day, unless you guys have a question. Hi, Allison. unless you have a question specifically for me, okay? Then stay around. Otherwise, have a good rest of your day.
Oh, look, here's the teacher.
Yeah, that sounds fine.
Okay.
Hello. She's muted. You're muted.
Oh, okay.
There we go.
Is-
Hey, so just hopping in for a second. If you guys get each other's information when you're done with that, you're more than welcome to end lecture for today. And if you have a specific question, you can come find me after class. You can't find me.
Okay.
Just meet me back in the main room. Okay.
Gotcha. Thank you.
Thank you.
Bye.